So this is an example of the conservation of momentum applied to a differential fluid element and ways that it might be useful to us. So here I have written the x and z direction momentum equations. Of course, there's a y direction one that is not on the page. And what we want to do is apply these to fluid statics. So this is going to be a stationary fluid. We're going to let gravity point down, and that means that z is our vertical component in the gravity direction. So as always, we're going to start with the most general form of the equations and simplify them. So if this is a static problem, what that tells us is that our velocity is 0 everywhere, which means du dt is 0. It means this term is 0 because u is 0. V is 0, so it's gone. W is 0, so that's gone. Gravity acts in the z direction, so there's no gravity in the x direction. And again, the velocity is 0 everywhere, and so there is no derivative with respect to position of velocity. In the z direction, let's go ahead and simplify that. Again, w is 0. The velocity is 0 everywhere, so the u, v, and w's go away. Gravity acts in the z direction, so that's going to stick around. And in the z direction, again, all the velocities are 0, so there's no spatial derivatives of velocity with respect to position. And so what we're left with from the first equation, if you look, a term did survive, right? dp dx. And so the first term tells us, the x direction equation tells us that dp dx is equal to 0. I didn't write it, but the y direction equation, of course, is going to be the same thing. And so the y direction equation tells us dp dy is equal to 0. And then the z direction equation, two terms survived, right? We have dp dz, and I'm just going to move it to the other side of the equation to get rid of the minus sign. And so that's going to be equal to rho g z. So this might look familiar. This first term says that pressure moving horizontal in a stationary fluid doesn't change, right? dp dx. That means for any value of x, p is the same. Any value of y, same story. But as we move up and down in the gravity field, not so much. In fact, we've already done the integration that turns this for an incompressible fluid into the following. P2 minus P1 is equal to rho g times Z2 minus Z1. And how would we do that? Well, you multiply up by Z, integrate both sides. And so that's a very simple example because there's not much going on, but it shows you once again how we want to cross terms out to start and then see where we end up.